All right, so we're taking questions on, let's see, 1, 2, 3, first page. Any questions that we need to talk about? Okay. 4 or 5? 6 through 8? 9 through 11? 10. Any others? 9 or 11? All right, so let's look at 10. Okay, let y equal this function, and I told y'all to omit it yesterday, but I think I figured out they just left the 1 off there instead of being a 2. It should have been 21. Right, but let's look at it anyway. This function has a hole. As it was written originally, it did not have a hole. What is the y value of the hole? Okay, so what creates a hole is when you have a factor top to bottom that cancels. So that's my clue. The fact that it says there's a hole tells me there's going to be a factor that cancels. So I'm going to factor the top, and those factors will be x plus 7 and x minus 3. And then the denominator is a difference of 2 squares, factors into x plus 3, x minus 3. Okay, so these two cancel. So where is the hole? At x equals 3 is where the hole is, because that's the value that would make that canceled factor be 0. Okay, so we want to know what the y value is at the hole. Well, technically it doesn't exist, but they're just saying, like, okay, if we could plug up that hole, what would the y value be? I'm going to take this leftover function, x plus 7 over x plus 3, and I'm just going to sub in 3. So that gives me 3 plus 7 over 3 plus 3 is 10 over 6, which reduces to 5 over 3. So that would be the y-coordinate that would basically fill in that hole and make it continuous if we needed to do so. Okay. All right, 12 through 15. Yes.
I just had a question about
13.
So,
okay.
I know that like you could have like a decimal, so you don't really know that it exactly has like 1 0, because like you don't know what like 2.5 is or something.
Mm-hmm.
But how do we know that it for sure has more than 1 0?
Okay. Let's plot these points that they give us, because that's a whole lot of details that we need to kind of look at visually. Okay, we have a continuous function on a closed interval 0 to 4. 1, 2, 3, 4. Suppose f of 0 is 1. F of 0 is 1. So 0, 1 is an ordered pair. F of 1 is 2. So 1, 2 is an ordered pair. F of 2 is 0. 2, 0 is an ordered pair. F of 3 is negative 3. And f of 4 is positive 3. Okay, so if we look at that visually, usually that will help. Okay, what else do we know? Which of the following statements about the zeros of f is always true? Okay, so if this is a continuous function and those are some ordered pairs, how many times do I have to cross the x-axis? Twice, because I'd have to continue through here and then back up to there. Now, could there be more? Possibly. But I know that there are, let's see what my options were, has exactly 1 0. That can't be true. And we're looking for always true. Has more than 1 0. Okay, that is true. We know it has to have at least 2. Has more than 2. It could, but that doesn't have to be true. Has exactly 2. It could be true, but there could be more. And none is true. So I'll go with that one as being the best option. Because more than 1, I know there has to be at least 2. Anything else on this page? Okay, 12 again, I would say let's graph the points. We have a continuous function on the closed interval 1 to 3. Oh, that's evenly spaced. Let's see. Let me go up to 2 and 3. Okay, I have a 0.12. I have a 0.2 something, some mystery number, and then the 0.33. Okay, so I know it's continuous. I want the equation g of x equals 1. What is this? Horizontal line y equals 1. Okay, so I have this horizontal line at y equals 1. Right there. Okay, the equation must have at least 2 intersections with this function that these 2 points are on in the interval 1 to 3 if k equals what? Okay, so I want a continuous function that contains these 2 points plus some other point when x is 2, but I want it to go through that line at least twice. Okay, so let's test them out. What if my ordered pair was 2, 0? Well, that would be down here. If that point is on my graph, do I have at least 2 intersections with the line y equals 1? Yes. What about if it's 2, 1? Well, then it's on the line, and that only guarantees 1 intersection. If it's 2, 2, then it doesn't even have to cross that line. It could all be above it. Same with 2, 3, same with 2, 4. So the only one that will guarantee that this graph dips below the line and then crosses it twice is this one right here. Does that make sense? Anything else through 15? Alrighty, 16 through 19. 16 and 17. Okay, we'll start with 16. Okay, anytime that we are approaching infinity or negative infinity, that's when we can examine highest degree over highest degree, because that's really the end behavior that it's looking for. Okay, and end behavior is what tells me also if I have a horizontal asymptote or not. So is this thing approaching a line, a particular value, or is it doing like this, or is it doing this? That kind of thing comes from examining as n approaches infinity. Okay, so highest degree over highest degree, 3n cubed over n cubed. As n gets super large, all these smaller degree terms become less and less significant. So these 2 terms are kind of dominating what happens to that fraction's value. Well, that reduces to just 3. If it reduces to a number, this is the limit, but it's also a horizontal asymptote. So if I was asked, is there a horizontal asymptote, this is exactly what I would do to determine it, if I didn't have a calculator look at the table or the graph. Okay, 17. If the function f is continuous for all real numbers, and if this is the function when x is not negative 2, then f of negative 2 equals. Okay, so I know plugging negative 2 in is not going to work, because that's undefined. But it's kind of like the question before. It's like, okay, well, if we plugged up this hole, what would I plug it up with? So what I'm going to do is see that this is factorable. That is a difference of 2 squares up top. I have a common factor that will cancel. So what's left is x minus 2. Now I'm going to take that negative 2 and plug it in. So negative 2 minus 2 is negative 4. So that would be my answer A. Okay, anything else on that page? 18. I was waiting for that one. Okay, if the graph of that function has a horizontal asymptote at y equals 2, perfect. It just followed the one I talked about, how you would find an asymptote. So if I have a horizontal asymptote of 2, that means that these highest degree terms simplify to 2. So if I have a over x, and that needs to equal 2, then what is a? 2. So a has to equal 2. Okay, and it has a vertical asymptote at negative 3. Well, the vertical asymptote, I'm going to look at the denominator. If x plus c is in the denominator, but I can't use -3, then what number is c? 3. If my denominator was x plus 3, then what would make that 0? -3. And that's the value that apparently I can't use because it's creating a vertical asymptote, so that means that it created a 0 in the denominator. So that tells me that c is 3. And then I just want to add a and c, so that gives me 5. All right, anybody for 19? Are we good there? Okay, 20 or 21? 20. Okay, so 20 you saw natural log and you went, I don't know. But actually you don't really have to know much about natural logs to answer this question. Okay, here's our function. It's a piecewise. Notice that this first part is from 0 to 2, second part is 2 to 4, but we want to find the limit as x approaches 2. And 2 is where the graph breaks. Okay, with this piecewise, I can have a couple of things happen. Maybe at 2, the graph is coming in this way, and it doesn't look like this. I'm just drawing two graphs. And maybe there's a dot there, but then this one does like this. Okay, could be jump discontinuity. Or it could be coming in, and then it goes back out with a different graph like that. Okay, so they could be connected, or they might not be connected at 2. So the way I find out is even though 2 is just part of this domain, I'm going to plug 2 into both of them, because that will tell me what I'm approaching here and what I'm approaching here. So if I'm approaching the same number, then I know that the limit will be whatever that number is. If these are approaching different numbers, then I don't have a limit. So let's see. If I plug 2 into this top function, well, that's natural log of 2. Okay, I don't even need to know what that equals. Natural log of 2. If I plug 2 into the bottom one, I have 2 squared natural log of 2, which is 4 natural log of 2. Are those the same? No, this one's 4 times larger. So that tells me I have a situation like this, where from the left and from the right, those y values differ. So that means I do not have a limit. Now, if I had natural log of 2 over here, and I was getting the same y value, then that would mean that they are meeting up at that point where x is 2. Okay, so I'm just subbing them into each function to see what those y values would be. Are they the same or are they different? Okay, any questions on 21? Okey-dokey. All right, let me stop that video, and then we'll start today's notes, and we'll record that.